Hi, in this video we're going to be talking about section 13.3, which is all about arc length and curvature. So the first thing you want to recall is that in parametric equations, we have an arc length formula, and I think you even see this in Calc 1 or Calc AB. The arc length was equal to an integral of the square root of f prime t squared plus g prime t squared all times dt from something like a to b. And I guess I should specify this is when we have an equation for the x coordinate. That's what's going on in parametric, and a separate equation, a separate function governing the y coordinate. This formula should remind you of Pythagorean theorem, and that's why it might not surprise you that in 3D, for vector function, a vector function r of t is like a parametric equation except in three variables. So in 3D, we have an equation like f of t, g of t, and h of t. We have these three functions giving us a vector function, and the arc length of this parametric space curve from t equals a to t equals b is going to be given by that same distance formula. So notice that we're taking the square root f prime of t, the x coordinate, squared, the x coordinate's derivative, the x coordinate's rate. And you can think of this as we're going to break down each component into its small change, a contribution of its small change over time, and we're finding the distance given by a small change. We're going to add up all those distances using an integral, and that's how we would get the arc length. A more useful formula, something that's nicer to remember, might be something closer to noticing that in 3D, one more time, if we start off with r of t is equal to f of t, g of t, and h of t, what you might notice is that r prime, that derivative, is the derivative of each component. This is covered in the last section. And then if we measured the length, how long is that tangent vector? You would get, how do we do length in 3D? We take, okay, we're going to take the length of each component, square them, add them up, and then take the square root. So arc length is also the integral, okay, again, just to specify the nouns here, the pronouns, arc length of r, that should have a hat also, arc length of r can be found by taking the integral of its small changes. This should also remind you of a distance formula. That's how you used to find the total distance traveled of a particle. That might be something we talk about in the next section also. In Calc 1, the total distance was the integral of the velocity. Sorry, the integral of the speed, right? The integral of the absolute value of velocity. And that's exactly what this is. This is the integral of the absolute value of the derivative, which is, in some sense, the velocity. All right, so let's talk about some examples. If I have a function r of t, and what we are thinking about when we think about these functions are space curves, that's 4 sine t in the I direction plus 3t in the j direction plus 4 cosine t in the k direction. Now, you don't have to know this immediately, but what's going on here is it's a spiral. I know that because we have this guy and this guy. That's making us make a circle type curve in the xz plane. We're talking about a circle in the xz plane. And what's this doing? It's making sure that we spiral out along the y direction and keep going that way over time. So we're talking about, I don't know, I'll just draw a brief sketch as best as I can. Something like that, some coil type function. That's always like a circle of 4 away. Circle radius 2 away from the y axis. That's sort of the direction axis. Find the arc length from t equals 0 to t equals 2 pi. So when you're given a prompt like that, what you're going to do is make sure you take the derivative, because you don't want to have to write these as multiple separate functions. Plus 3 in the j direction, minus 4 sine t in the k direction. You want to find the length of that. So that's going to be 16 cosine squared t plus 9 plus 16 sine squared t. In my experience, a lot of students come into this class not really understanding how to simplify the trig functions here as easily, so please just follow along. What we have here is 16 cosine squared and 16 sine squared. What you might remember, and if you don't remember this, you need to remember this, is that cosine squared t plus sine squared t equals 1. So it's always true that a cosine squared t plus a sine squared t, notice I sort of multiplied this left-hand side by a, should equal a. If that doesn't make sense to you, I've also explained it this way, and sometimes students catch on better now. Right? That should be a times 1. Why am I talking about this? If you're missing the beats here, that guy plus that guy is going to equal 16. Okay, so just make sure you remember your trig identities, especially the Pythagorean one. So that's 16 plus 9, which is just root 25, which is 5. So what does that mean? What does this mean? Well, it just means that the length of the tangent vector is a constant, right? The length of these tangent vectors are always 5. It means, realistically, that this arc length is going to be really easy to compute. So we're going to do 0 to 2 pi of 5 dt, which is 5t, evaluated from 0 to 2 pi, which is, of course, 10 pi. And for a circular type spiral, that should make some sense, right? All right, let's do one more example here. I did too far. If we have a more complicated function that I'm not even going to attempt to draw, e to the t cosine t, e to the t sine t in the j component, and then e to the t in the z component or the k component from 0 to t to 2 pi. All right, so right now, as you've been following along, this should be doable for you. make sure you carefully use the product rules and give me R prime. Find R prime, see what you get, test your knowledge right now. Pause the video. 3, 2, 1. All right, you should have gotten something like negative e to the t sine t plus e to the t cosine t, e to the t cosine t plus e to the t sine t, and then e to the t in the last component. It might be helpful to notice that what's going on here is you can factor out some e to the t's. So we're just going to rearrange this a bit. We're going to have e to the t times cosine t minus sine t, e to the t times cosine t plus sine t. I'm just going to try to show you another algebra component that can happen. So when we try to find the length of r prime, what we're going to get here is this whole mess squared plus this whole mess squared plus the last guy I can square pretty easily on my own, right? E to the 2t, and you don't want to forget that square root house, that square root symbol. So how is this going to simplify? Well, draw the house at the end. E to the 2t cosine t minus sine t quantity squared plus e to the 2t cosine t plus sine t quantity squared plus e to the 2t. I hope we all see where that's going on some level. The auto draw feature messed me up. Oh, forgot a bar there. What I mean by where that's going is we can easily factor out that e to the 2t. And when I say factor out, I mean factor out the whole entire square root. E to the 2t, e to the 2t, e to the 2t. We're going to factor that out and take the square root to bring it to the outside. So that's e to the t and then times the square root of what's left over, which is cosine t minus sine t squared plus cosine t plus sine t squared plus 1. That 1's really easy to forget about, right? So if we start foiling this out, if we start foiling out each of these or distributing, you're going to see a very nice cancellation. I recommend you try that algebra out yourself before watching me do it. Or you can try to think about how it's going to go, because it is really a very nice situation here, to be honest. 3, 2, 1. Cosine squared t minus 2 sine cosine. Obviously that's the same if you write 2 cosine sine plus sine t squared. And again, the real hard part is to not leave the 1. Cosine t squared plus 2 sine cosine, just to make sure it looks nice, plus sine t squared, sine squared t plus 1. All right, so the main thing to look at is these two cancel. And then we have 1 cosine squared plus 1 sine squared, and even a second cosine squared plus a sine squared. So how does this simplify? It's just e to the t times root 3. Wow. How much fun did you have doing that? All right, we're going to shrink it because that's only half the work. So the arc length is going to be the integral of e to the t root 3 from 0 to 2 pi dt, which is, of course, e to the t root 3. Very nice antiderivative formula, which is e to the 2 pi, root 3 minus root 3. Okay? Or e to the 2 pi minus 1 quantity root 3, right? So that's the main thing to look out for when you're doing this kind of thing. There's going to be some nice cancellations. You're going to see some really, I don't know, interesting is probably not the right word, but sort of algebra that can happen. I will point out for your homework, just to help you out, if you see something like this, I'm just going to point out this, e to the negative t, these things are going to square in interesting ways that you may not have seen before in a while, right? I would get e to the 2t minus 1 plus e to the negative 2t. I hope that's clear to you what's going on here. It's because when you try to do this multiplication, e to the t times e to the negative t is going to equal 1. So I'm just going to point out to you, if you start seeing things like e to the 2t minus 2 e to the negative 2t plus, or, I mean, you could try this out yourself. Make sure you can see how this would FOIL and make e to the t plus 2, e to the 2t plus 2 plus e to the negative 2t, because those are weird kind of factorizations that you almost never see. You're still, to go back to like algebra basics, you're still looking at, oh, it's a square in the front and a square in the back. It might be a perfect square, but it's because of the exponentiation laws that you're getting these ones showing up. So that's just a fair warning for your homework. I don't know, please try those problems out. They can be easily done by hand only if you start seeing stuff like that. A lot of the times for arc length, we're going to rely on a calculator, but you shouldn't have to in certain problems like what you see on the screen. All right, that's enough for now. Good luck on your homework. I'll see you in the next one. Bye.